So good evening, everybody, and thanks for letting me in and for the organizing to this very interesting workshop. I think I have the honor and pleasure to give the last talk, and thank for all of you that is still there. And so this is going to be a talk that done in collaboration mainly with Tossenbecker and Klein Conrad and Lorenzo. And I'm going to skip the topic. I'm moving more on the line of Carolina talks on discussing about mantle convection. Well, what we know about mantle convection, basically, I think we arrived, and probably Carolina shows something about that. A good idea, a pretty good idea of how the convection work in the beneath the oceanic lithosphere. And those are, for example, some of simple model run for basal traction, for triggered by density, where you have the blue solution that is the mantle, and the orange one is the GPS or the velocity of plates. So beneath the ocean, we pretty know how it convection work. But it's much more uncertain how convection work beneath continent. For example, here I bring two examples from trying to understand in the Colorado Plateau enigma of the elevation, and one is on the left is Robert Much experiment where you can see that to match some of the elevation of the area, they match with a large-scale flow solution for the entire mantle. And on the right, for the same problem, there are people that are involving more shallow, small-scale convection, triggering a lithospheric instability. So because of the slow motion of the continent and the heterogeneity in the lithosphere, we don't really have a good picture how mantle work there. So the basic question, I think, still hold on the floor. What is the role? How can we imagine the mantle convecting beneath continent, and what can be the role of mantle convection driving, for example, collisional plates such as the Himalaya? So for trying to discuss about this point, I would like to bring you on a journey on the Tethyan Belt, actually, which is the belt running from Mediterranean down to Indonesia. And the point I would like to raise here is that it's probably we can, looking at the formation of the style of mantle building, we could infer and having some indication about the style and the scale of convection in the mantle. So let me start with this beautiful geological map done by Manuel Poubelier. Here the color just meant to represent the time of accretion of a block. So when you look at this mountain belt, I mean this Tethyan belt, I mean you have a protracted long-term accretion of crustal block running from the Paleozoic down to very recent age that accreted one each other and stack and forming this beautiful puzzle. And what is interesting when you draw a section here, just to take you an idea of what we are looking for, and looking from a cross-section from in Arizona, about from the Himalaya to the Tibetan Plateau, and one on the Alps, the same scale, actually, you look that we are facing processes that are probably different in terms of scale and intensity, of course, along the same belt. So geodesy, this is, I think, a wonderful compilation that show up how this two block, Arabia and India, is intruding and indenting within continent and Asia. And what was also very interesting to note is this kind of a symmetry where we have the escape of flow of crustal material away from the subduction zone, giving birth to this beautiful toroidal symmetric scale to a subduction zone, one in Aegean and another one in Indonesia. But you also may notice that the entire deformation is spread over a wide area and in diffuse fashion, actually. The main problem that is still standing on the floor is the fact it's not that the problem of that collision. I mean, we know that India separate from Madagascar, Seychelles, and then run very fast against Asia, reaching velocity of about 18 centimeters. This is the velocity versus time here. But the problem is still that for example, the Alps, Arabia or India, then you have just after collision, you still have a protracted velocity of indentation. This is a mystery for me, because US supposes that once a block arrives to collision, then the force resisting its motion will be overcome the other forces, and then everything stops. Instead, Indians keep going at 5 centimeters inside Asia. And that is a problem, and we don't really know the answer of that. So to let you introduce to the topic, maybe it can be useful, Carolina already done it, give a look to this simple picture, oversimplified picture of the force at work here in the system, inspired by force Ayurveda, of course. The black is the acting force, the red is the resisting, so all of them act against this one. The first force acting is slab pull, is if you scrape off the crust from the mantle lithosphere, then you can have some slab pull forces acting that drive continent. That's fine. Second is the ridge push. Everybody knows this is a potential energy stored within different elevation within the ridge and the more deeper part of the abyssal plane. The third is the mantle flow that can make for density and convection drag the plate on top of that. And the fourth is plume push. It's a recent, there is some work showing that when a plume plays in the mantle, it can lubricate at the base of the lithosphere, it can give a hit to the continent and pushing against that for a temporary stage. All them are against the crustal thickening. So this is basically a gravitational potential energy force, and to store and to sustain the mountain, like in Tibet, 80 kilometers of crust, you have to keep going with all these forces acting at the same time. And the number we have for this number 5, resisting force, that tends to be equilibrate the other, is about 10 to the 12. So it's not a big, a small number. So let me review first very fastly what is slab pull force. This is a work by Fabio Capitano, for example, very nicely exploring the decrease in slab pull. Theoretically, from very simple model, can fit fairly well the decrease in the velocity of India, but it doesn't know at all fit the protracted velocity of after the collision take place, so this 5 centimeters per year. And in addition to that, slab pull probably is very moderate between collision zone because multiple episodes of break-off take over, and therefore we don't really have a slab really pulling down. And in addition to that, slab pull is not favoring advancing trench, but retreating trench, therefore is work against collision. Ridge push, there is plenty of good work done on that topic. For example, I take one from Ghosh et al. 2006, demonstrating that to sustain the Tibetan plateau, the ridge push is not enough. You need additional forces, and these additional forces, we don't really know where it come from. So just simply to review all that, we think ridge push is probably too small, slab pull too small again, plume push is probably time dependent, so it maybe help to speed up during the first phase of the formation the velocity of India, but then it should be decreased. So what left? Probably mantle drag is an interesting candidate in addition to the other. Then may explain that. So what we can do? Is to try to run mantle circulation modeling, and with the help of that kind of model, we can try to infer what can be the prediction for the velocity of the plate. So basically what we're doing, and Thorsten Becker is the main actor here, is to run in very simple model, global model, using sitcom, and basically based on the idea that the mantle work is incompressible laminar flow, solving simple equation and assuming the boundary condition that the surface and the core is free slip. So we may work a little bit in the rheology, but at first sight I would like to say that for a Newtonian solution or for a temperature-dependent viscosity, let me say that the first order solution are pretty robust, and then we impose the plate boundary weak. So the main assumption behind this exercise is basically that we take from tomography the anomaly and we convert it then to temperature. And this is directly to that, without looking for the best solution and without any try to fit the plate velocity in a specific way. So this assumption implies that we don't really consider chemical anomaly and beside continental kills. And this is a very strong assumption, of course, and we do know that it's probably not true for the large low velocity shear zone at the base of the lower mantle, but in principle, for the overall scaling is probably robust, and Carolina already comment on that. And we also try to make some solution only prescribing density anomaly along the Vadati-Benioff zone, if to check whether the influence of the subduction zone slab pool can influence the system. Basically, what we're doing here is that we zoom in a specific region and we try to compare the result with the geodesy, with plate and microplate motion, with the deflection on the surface, so with the residual topography, comparing the result of dynamic topography with residual topography, and check it with mantle anisotropy. But unfortunately, I have no time to discuss too much about that. So we'll explore first the region that I like more is the Mediterranean, and then we're going to zoom out into the Tethyan system more in general. So let me introduce you to the Mediterranean. This is a map diagram showing the GPS in yellow with respect to Eurasia fix, and we have this beautiful pattern of counterclockwise rotation that is well known. Arabia is moving northward, but Anatolia is accelerated 2 or 3 centimeters per year toward the west, so that again Aegea is moving even more toward Africa or Nubia, so that giving rise to this interesting trend. But also this small plate here called Adria is playing a very bizarre role, is moving away from the subduction zone, and both microplate are moving irrespectively to the overall convergence frame between Nubia and Eurasia, which is rather in this direction, and is very, very small, as you may see this little arrow here. This can be a representative of the Nubia motion. Actually, we don't have a lot of data on the African coast, as you may imagine. Also, here plot the seismicity, and it's with the color is scaled with the depth. What is interesting here is to know that overall we have the largest scale seismicity is just on the crust. There is very few seismicity in the mantle. This is a little Vadati-Benioff zone here in Calabria that is plunging down to 400 kilometers, and another one that is on the Aegea that is plunging down only to 250 kilometers. So that means that we don't really facing a plate convergence like in a Pacific style fashion, but the formation is distributed over a wide area over the cross. So it's a classical diffuse plate boundary. So the question is, why does microplate move like that? I mean, and why accelerate with respect of what moved fastly Anatolia here, Aegea here, what uprising plateau here in Anatolia, in Iberia? There is a lot of questions that rise looking into the dynamic of this little system. So this is the result of our model. I fastly explain how we run it. I mean, this green line is the plate boundary. We assume a simplified plate boundary. This is weaker than the surrounding lithosphere, a factor of 10, something like that. The gray arrow are the imposed velocity. We impose the motion of Nubia, it's very small, and we also impose the motion of Arabia, sorry. And the yellow arrow are the geodetic velocity you already seen before. So when the white arrow are the result of our model, we let this plate free to move whatever they want under the convection and the convergent margin. And the background color is a kind of dynamic topography result. So what you can see is that we can do a good job here in Anatolia, is moving in good direction toward the west. We do a terrible job here in Aegea. Also, Adria is not fitting very well. So this is why you showed me that. I mean, we think this is an interesting result because this area is very highly resolved in terms of topography. Here we use a model for MIT, Lee van der Ilst, 2008. And this is a section of this model, a profile like that. And when you look at the section, what you recognize that you have this big upwelling in the Middle East. It's producing this big signal in dynamic topography. And then you encounter the Hellenic subduction zone here and the Calabrian subduction zone here. So the flow is running this way. The slab is rolling back, so that's good, the solution that we imagined. But then it uprises again, and then it's going down back, and it uprises again in the Massif Central, which is a kind of return flow of the Calabria slab. So, and giving rise to this small-scale dynamic topography. What is interesting here is that what we're seeing here is that if the resolution is high enough, we can able to capture signal on the wavelength of convection that is in the order of 100, 200 kilometers. And it's pretty good. And also what we can see here is that all this convection is forming little cells that are basically confined between the base of the lithosphere and the transition zone, which is pretty interesting, I guess. It's a new images. And then you can capture this signal better when you look at these lights going down to the mantle. Then we have the blue going down, the red is going up, forming this little blob, so up and down. But when you arrive at the base of the 660, nothing more disappear, only the phase of the deep slab and the Hellenic trench falling down here. But basically, you lost all the track of this small-scale convection. So we found it pretty interesting. We can improve our model. We can, of course, say that the Alps is coupled, so this is a better solution for Adria. It's falling the direction now. The white and the orange is good very well, but we can work on that. But this was not a message. The message was to try to capture, with the resolution of the tomography we have here, the style of convection at work here. And we can also work with anisotropy. I'm not going to spend too much detail on that, but try to fit the large scale. There are a lot of data you may see of anisotropy, SKS basically, and the blue is a good job and the red is bad job, and you can try to match whether the simulation of the convection we are using is fitting the prediction of the anisotropy in the mantle or not. And this is a solution using tomography plus implementing the density signal in the subduction zone. Then we can also work for dynamic topography. There is one of this model by using tomography by Lapo Boschi in 2011, where you have this small-scale convection here. This is the residual topography using one of the crustal model, which is pretty uncertain. That is the topography filtered by the crustal isostasis plus some lithosphere. And you may see that there is a good match, and we geologists will be very happy when you go and look at the resemblance of that signal, for example, in the field, where you can reinterpret, for example, the formation of the high mesetas, pretty undeformed area, standing a kilometer elevation in Iberia, for example. The Iranian plateau or Anatolian plateau can be explained, maybe also partly, as such an effect of the mantle convection. So, as a summarizing a little bit what we had, it just we found that I think this is an image of what we think is running here in the Mediterranean. When you look in detail in this area, we found that the small-scale convection can be representative of the style of subduction we have it, and this is explain also the very fast intermittent episode of back arc extension we have in the Adria. But going more to the larger scale. Okay, this is the reference tomography that we have to use, because this is as mean, and we can go better than the Texas solution, but the solution, the result, I will tell you, is really similar to that. And this is the resolution jump we are looking for. This is what we were doing before in the Mediterranean. This is the resolution of our tomography, and this is what we are working now. So, of course, our result will be very dependent on what we put into the box. And this is the result, basically. So now I have to explain a little bit this picture. The yellow is the plate boundary that is following bird, whatever, plate boundary. So again, it's a weak zone, about order of magnitude weaker than the surrounding mantle. And then we let all the plate go in whatever they want in an inertia fixed reference frame. The white arrow are the result of the plate motion, and the orange one is the result of the GPS. So you may compare directly what is the arrow with the white with the orange. And what we found is pretty good. I mean, we're very excited by that. So looking at indeed using a very simple tomography model and without making any effort to implement for plate motion, we had a very good solution for India, for example, that is going the right direction at a pretty much a good rate. And we don't really have the return flow here as in the GIA. It's something that we miss. But India is indenting, and this was one of our main worry. And also, you can find that Arabia is also doing the same thing. So it's moving toward the north, toward the subduction zone, indenting into the Zagros. We had a terrible solution for Africa, which is moving completely different from what we expect. Maybe Carolina can think about that more. I don't know whether you have a solution, but it's going completely in another direction. Maybe we didn't consider very well the effect of Cradon. And also maybe Australia is not good. But we test also taking Africa fixed, and I tell you, it doesn't change a lot the result. The message here is that when you go at 200 kilometers, you may understand better what happened. Is that you have two uprising, upwelling point, Afar and Carlsberg Ridge here, that are very well-known upwelling site, and two subducting area. This is the Tethyan slab beneath Zagros, Himalaya, and between the Tethyan belt. And those two systems is joined together and make a conveyor belt, and this conveyor belt is just dragging continent against the collision zone. So it's doing this in India, for example, is very nicely expressed here, uprising in Carlsberg Ridge, downwelling in the Tethyan slab, and you do this conveyor belt in the whole mantle convection. That's interesting. This is something that arises from mean. You see, it's a broad, it's a kind of very broad, robust solution without without pretending to be high resolution. But what is interesting is that if you put, for example, another solution like the MIT one, then you don't have anymore the Carlsberg Ridge here, and the result are that India is not moving anymore. So that means it is really a job done by the concurrent action of an upwelling source here and downwelling source here that is arriving to have the solution that we express here. And I think this is an interesting message. This is exploring the role of this large-scale convection cell that is bringing pieces of continent between and colliding between the Asia. So we can also work on the residual topography here. We have an extreme residual topography in Afar. I think this the partial melting process, it's clear an explanation, because otherwise we should really have a too high topography. We don't really have a large signal of uplift. Actually, in Ethiopia, I think we are in the order of a few hundred meters. So you can match the residual topography with dynamic topography. We get a signal in Carlsberg Ridge, Ainan, for example, looking for Baikal. So we can have fun with that and try to work better on the interpretation of this stuff. So as a summary for this game, we think we may see that India, for example, is slab is not sufficiently able to drive a collision. So slab pool hypothesis cannot work and work against the slab pool against collision, not for collision, and for the case of India. So the only process that may explain properly the immersion of India in time and the protracted collision of India is this conveyor belt that's acting on world-scale convection. So we start looking at two different sides of images. So let me zoom again a little bit more to the entire, our Tethyan belt is rather here, and taking as mean and looking at tomography model, I think we all know about this large low-velocity shear zone at the base of the lower mantle. This is a well-robust signature, and I think this is very interesting images raised by several people with several authors. When you look at for the Tethyan belt, you have to go up 1,000 kilometers. Then you have this suture zone that is stalling into the uppermost part of the lower mantle, running from the Hellenic Trench to Indonesia. And on the other side of this large low-velocity shear zone that almost disappear here, but with some of the points are here, you find the Cordillera slab that is the Farayon that is going down and reaching the Cordillera here. So what you have is what Anne defined the Indo-Atlantic box. I think is a very good denomination for this area. You have upwelling here, or a large low-velocity shear zone that produce upwelling here, and the two downwelling here. They are closing really a system. As if it's very close, then it probably should interact together. And this is an interesting stuff to explore. If you do an equatorial section here, then you may have this kind of picture that you can find also in textbook, and it's pretty well known. I mean, you have the upwelling in Africa, superswell, the Pacific swell on the other side, and the two downwelling side, the Tethyan belt here is merging the Pacific, because of the projection, and the Cordillera slab here it's going to. So you can define the convection cell, and I think in this paper, for example, is discussing very well, Adam and Barbara and others, this process of this degree 2 convection that I think is a fundamental aspect of our planet now, present day. But what is fun is that if you put the geology on top of that, then you run into trouble, in the sense that, for example, if I pose here my trench position in time from the late Cretaceous to the Tertiary, you may find, for example, that the position of the trench 90 million years ago do not fit the sutured zone that I have into the lower mantle. And this is because that means that probably the Cordillera slab arrived at that depth further on after, like 50 million years ago or 40 million years ago. And this is a deposition of the trench now fit fairly well on the line up with the deep anomaly. And the same can hold for the Pharaon that probably entered into the lower mantle at this age. And also for this kind of game, although here in the Tethyan belt is more complex. Therefore, we can try to, for example, with the imagination of our imagination geologists, we can try to figure out how was the system working in time. This is the present day solution with a flow line directly from our flow solution model with this upwell, the African swell. Of course, this is a chemical pile, it's now moving, but the rest probably it is. And this is producing this convection cell. You have the Cordillera slab that where we're going in Bolivia is very well anchored in the lower mantle. On the other side, you have the other convection cell, you have the Tethyan slab, which is standing back on the present-day sutured zone in Himalaya. But when you go back in time, you probably have a solution 60 million years ago where the Atlantic was spreading, for example. At that time, we had the departure of India that started running very fast. The Deccan leap and place, the India go very fast again, the slab. And at that time, probably the slab will start penetrating the lower mantle. And this is stalling the circuit. And once the circuit is stalled, that ensures the fact that India can keep protracting, going within Asia, forming these huge, enormous anomalies, thick pile of crust as we have in Tibet for 80 kilometers of crust for 1,000 kilometers of length. So you need really a big effort to do that. Then in this kind of game, instead, the Cordillera was not entering already. South America was going very good. Toward the east, and the west, and the slab is probably rolling back. So no deformation, no Cordillera. The Andes was not formed yet. There was an extensional basin forming here in the back-arc area. So there was no mountain. To have the mountain, we do have to expect that the slab anchoring the lower mantle for some reason penetrate in stability. At this moment, then the South America have hard time to keep going in this direction, at least here in Bolivia or Klein, and where you have a immersed thickness part of the Andes. And when you penetrate here, you start installing again the large-scale convection cell, and you may have the residue of this upwelling in Ethiopia, for example, Lipe, which is very well known, but other large igneous provinces was erupting at the moment. So the upwelling and downwelling go together very well, I think. And then you reach the present-day solution, actually. So I would like to just conclude very simply. I think what we have beneath continent, if the resolution of the tomography is fine enough, then we may be able to detect a multi-scale convection. One is a small scale that is really working nearby the subduction zone with little upwelling, scale about 100, 200 kilometers, confined into the uppermost part of the upper mantle, from the base of the lithosphere to the transition zone. And this is kind of game that is playing it could play a big role, for example, in the back-arc area. But in addition to that, with a larger time scale, we probably have to figure out another cell that is working at the larger scale. And this may be activated episodically and may last for some tens of million years. So the two multi-scale convections should work together. This is the images, then I finish up. I think that wool mantle convection is ensured by the fact that between Africa and India, with a strong plume-associated upwelling component that we have up there, and sustain it with the downwelling. So you produce this large-scale circuit convection. This ensures for having a protracted collision and formation of big mountain. And similar setting, we think we can hold also for the other side of the Indo-Atlantic box, that is the Africa-South American system. If it's true, the story, then we maybe use the mountain belt or the episodic formation of mountain belt and crustal thickness just to detect what can be the story of the mantle with a big episode overturning, alternated with episode of maybe more simple situation. And inspired by Clint and Carolina, I would like to finish up by thinking that the mountain can tell us a lot about what is the style of convection. We really think that this is a bottom-up kind of tectonics also for us, doing with tectonics and structural geology. And there are two end members here, and the scale of the two cross-section I showed you at the beginning can be sustained that. We can have a slab pool orogeny, the Alps, for example, or the Apennine, where you have this little slab orogeny. This can be related to scraping off the crust during rollback with a flow line and a small-scale circuit. And this is other things, is that the slab suction orogeny, where you really have all the mantle convection that is producing a kind of scale of thickness. This, of course, are two end member, and we can have an infinite solution in between. Thank you very much for your attention.